Hello and welcome to full course session on Basics of Mold Design, your comprehensive guide to understand core principles of mold design and injection molding. This is a certified course session, so don't forget to fill out the form in the description after completing the session to claim your certificates. Share your achievements proudly on LinkedIn to showcase your new skills and take a new step forward in your career. At Skill-Lync, we specialize in providing industry-relevant, advanced training programs tailored to help you excel academically and professionally. This course has been designed in collaboration with experts to equip you with the foundations and technical knowledge required for success in molding design and manufacturing. Before we dive in, make sure to subscribe to our channel for more insightful tutorials and updates. Hit the subscribe button and stay tuned for more industry-focused contents. Here is what we'll cover in this exciting course on Basics of Mold Design. In the first chapter, you will begin with the basics of injection molding. You'll learn what injection molding is and how to play a significant role in modern manufacturing. We dive into mold cycle, exploring various stages and how it influences production efficiency. This chapter also introduces you to the difference between thermoplast and thermosets, along with their application in the industry. We will discuss various plastic processing methods and provide insights into a current scenario of the mold industry. Additionally, you will explore the roles of engineering plastics in automobile and gain a comprehensive understanding of plastic material properties. In the second chapter, we'll shift our focus to the basics of mold design. You will gain an in-depth understanding of the product development process and its stages, along with the various departments of mold manufacturing industry and how they function. We'll break down the parts of mold, explain different types of mold used in industry, and introduce key design elements like draft angles, parting lines that are essential for creating high-quality molds. In third chapter, we will explore design for manufacturability and defects in injection molded components. This chapter will cover mission tonnage and its importance in mold design process. You will also learn the principle of DFM, ensuring that your designs are optimized for efficient production. Furthermore, we will discuss common defects in injection molded components, its causes, and strategies to prevent them during the design and manufacturing stages. In the final chapter, we will focus on the concept of parting surfaces. You will learn about the types of parting surfaces and see practical examples to help you understand their applications. We will also cover how to ensure matching drafts in mold design, account for shrinkage during molding, and explore the roles of inserts for achieving durability and precision in molding. This chapter ties together all key concepts to help you master the fundamentals of mold design. Thank you for joining us on this incredible journey. By completing this course, you will gain a solid understanding on mold design fundamentals, setting the foundation of your success in plastics and manufacturing industry. Make sure to subscribe to our channel for updates and more in-depth tutorial on mold design and other engineering topics. Complete the course, claim your certificates, and don't forget to share your compliments on LinkedIn. Now let's get started with Basics of Mold Design, your first step towards mastering the world of mold design and manufacturing.
Hello guys, hope you are doing good. Welcome to the first session for the mold design course using SolidWorks. In the first few sessions, we will mainly look at the theory behind the mold design, and in the subsequent sessions, we will be designing the mold using SolidWorks. In this session, we will be looking at the basic working of the injection molding process, learning about the mold cycle, thermoplastics and thermosets, plastic processing methods, and we will also have a look at the current scenario of mold industry, engineering plastics, and properties of plastics in brief. The first topic we shall cover is what exactly is injection molding. Injection molding is a manufacturing process in which parts are made by injecting molten material into a mold. The hot molten material which is injected takes the shape of the mold and then solidifies as it is being cooled. Then the mold is opened and we get the required part. Here we have an animation showing the basic working of the molding system. I will first run the animation so you guys can see the working, and later I will explain the working. The raw material used for injection molding plastic parts is plastic pellets, which are called as resins. This resin is dropped in a hopper, and through the hopper, it goes into the injection barrel. In the injection barrel, the plastic pellets are driven forward by the rotation of a screw. As the plastic moves forward, it melts due to the friction and gets converted to molten plastic. External heating may also be provided in some cases to melt the plastic. Then this molten plastic is injected into the mold through the nozzle. The molten material fills the region between the core and the cavity, where it takes the shape of the mold. The core is the convex region which forms the inner surface of the component which is being molded. It is also referred to as the male portion of the mold. The cavity is the depression or the concave region which forms the outer surface of the component. It is also referred to as the female portion of the mold. The material filled between the core and the cavity is allowed to cool for a while so it solidifies, and then the part is ejected from the mold. There are also many other parts that form a part of the injection molding system, which will be discussed in the later sessions. Now, there are many different manufacturing processes for creating plastic parts, which will be covered in brief in a while, but there are some distinct advantages of using injection molding process. First is that injection molding can be used to create very detailed and complex geometries with high accuracy. Also, this method is very fast compared to other methods which allow for high production rates. It is also possible to add additives to the feed to impart greater strength to the plastic. We can also use multiple plastic types simultaneously in injection molding, and it is also possible to automate the entire process, allowing for lower manufacturing costs. Due to these reasons, injection molding is preferred in industries for making plastic parts. One of the latest technologies introduced in injection molding is micro-injection molding. So if you need to manufacture any parts in micro tolerance, then this method can be used. Here in this image, we can see that the hole size required was 250 microns. For making such small features, micro-injection molding process can be used. These parts may be used for medical applications or high-precision mechanical devices like watches. Now, what is mold cycle? The time required to complete one injection molding process is called mold cycle. There is no fixed formula for calculating this mold cycle time. It depends on a number of factors that I will be explaining in this slide. The first factor is number of cavities. The number of cavities is the number of parts that will be produced in each cycle. So it's not like only one part can be produced in each cycle. It is possible to create 2, 4, 10 or even 64 parts using a single tool in one single cycle. And more the number of cavities, higher will be the cycle time. The second factor is the type of material. A number of materials are available for injection moldings like ABS, polycarbonate, plastic, and many more. Now, different materials will have different material properties like different densities, which will affect the cooling time for the molten plastic. And more the cooling time, more will be the mold cycle time. To explain the next few factors, I will have to first explain what runners and gates are. Remember, I mentioned how the molten material passes through the injection barrel and moves to the mold. There are also other components present in between. From the nozzle at the end of the injection barrel, the material first enters the sprue. You can see the sprue on the image on the right. Now, sprue is basically a large channel in the mold which receives the molten material from the nozzle. This sprue channel gets divided into a number of smaller channels called a runner. This runner carries the molten material to each individual section of the mold, and the connecting channel between the runner and the part is called the gate. So the next factor is runner removal. Now, since runners are not part of the component required, they have to be removed, which results in an increase in mold cycle time. Runners can be removed manually or by using robots, but for lower mold cycle times, use of robots is preferred. Runner type and gate type. There are many types of runners and gates available which can be used in injection molding, which will be discussed in further sessions. So the type of the runner or gate which we select will also affect the mold cycle time. Geometry. The thickness of the part manufactured will also impact the mold cycle time. If the thickness is more, then more cooling time will be required to solidify the plastic, and thus more cycle time required. This refers to the design aspect of the mold or how well the mold is designed. Let's take the length of the runner channel as an example. We know that runner channels are provided for the molten material to reach the cavity. But how much should be the length of the runner channel comes into design considerations. If we provide a runner channel more than the required length, then that would increase the mold cycle time. So how good the design of mold is will also impact the mold cycle time. The injection molding machines are primarily classified by the type of driving systems they use. The driving system can be hydraulic, mechanical, or electric. So the type of machine used will also impact the mold cycle time. Electric machines have been found to be faster and also more accurate, but they are also the most expensive ones. All plastics can be divided into two major types, thermoplastic and thermoset. The primary difference that you need to know between these two types of plastics is that thermoplastics can be remelted back into a liquid repeatedly, whereas thermosets once shaped cannot be remelted. This happens because when thermosets are heated, the polymer chains are attached together with a process called cross-linking, which gives it a permanent 3D shape and makes it more resistant to melting. But since thermoplastics do not form this cross-links, they can be easily melted. This property of thermoplastic makes it easier to shape, and that is why for making plastic components using injection molding, we use thermoplastics. Most of the plastic components used for making a car, around 90%, are also thermoplastics. An example of thermoset would be your cooker handles. These handles are made from bakelite, which is a thermosetting plastic. In general, thermosets are stronger than thermoplastics. That is why you can find thermosets in safety equipment like helmets, and is also used for heavy industrial applications like load bearings. And as thermoplastics can be remelted and shaped into other components, it is recyclable. One of the disadvantages of using thermoplastics is that it cannot withstand high temperatures. So applications where high temperature resistance is required, for example, engine parts, landing gear for planes, or satellite components, thermosets will be preferred. And also very high surface finish can be acquired using thermoplastics, which is not possible in thermosets. So in application where good surface finish is required, like interior of luxury cars, then thermoplastic will be used. Let's move on to the plastic processing methods. Injection molding is not the only plastic processing method available to us. There are many other methods as shown in this slide, and I will be giving a brief explanation on all the processing methods. But we won't go into much detail as the focus of our course is the injection molding process. For thermosets, we have compression molding. In thermoplastics, we have injection molding, rotational molding, extrusion, vacuum forming, blow molding, and gas-assisted injection molding. The working of gas-assisted injection molding is the same as injection molding, which was covered in initial slides, but here an additive is added in the form of a gas. When making components of high thickness using the injection molding process, small craters are produced in the part due to shrinkage of plastic. This is a defect known as a sink mark. We will be covering all the defects formed in the injection molding process in the later sessions. For now, you need to just understand that in gas-assisted injection molding, a gas is added to the feed of the system to avoid the sink mark defect. This is the diagram for compression molding. In compression molding, the core is fixed and the cavity plate is moving. This is the opposite of what happens in the injection molding, where the cavity is fixed and the core plate moves. The material which is to be processed is placed on top of the core. Moving cavity plate will compress the material and the desired shape will be obtained. Compression molding is usually used to make rigid and hard to break parts like pot handles. Rotational molding. Here we see the powder is placed in the shell first. The shell is then closed and the system is rotated. Heat is applied from the outside and this results in the formation of component in the outer edge. The part is then cooled and ejected from the system. Rotational molding is used for creation of hollow parts like toys. Extrusion. In the extrusion process, the material is placed inside a container. A ram forces this material through the die to acquire the desired shape. Pipes, window panes are usually made using extrusion process. Vacuum forming. This diagram here is not an accurate representation, but it still explains the general concept of vacuum forming. In vacuum forming, a plastic sheet will be placed over the mold and it will be clamped using some mechanism. Then the sheet will be heated, which will make the sheet more flexible to move. The vacuum formed at the bottom of the container will pull the sheet and the sheet will take the shape of the container. Food containers is one example of vacuum formed part. Blow molding. For the blow molding process, a molten tube of plastic is extruded from the machine and placed into the mold. The pressurized gas is blown into the tube and the plastic captures the profile of the mold. Water containers, large drums are some of the parts that are made using blow molding process. Now we will look at the current scenario of mold industry. Molding is a very important process in industrial production. Now molding can be in the form of plastics, it can be in the form of die casting or in the form of sheet metals. For the formation of plastic components, injection molding is the most frequently used method. For making sheet metals, press tools are used, and for die casted components, high pressure die casting and low pressure die casting machines are used. Among these things, plastic specifically plays a very important role. The development of lightweight vehicles is an inevitable trend that will effectively promote the development of plastic injection molding. According to statistics, more than 95% of parts of the car need to rely on mold for batch processing in the development of a new car. This includes around 20,000 auto parts, including sheet metal parts, die casting parts, stamping parts, plastic molded parts, electronic components, and so on. In the development and manufacturing of these parts, a large number of molds and fixtures are required, and the demand of molds is the largest item. Therefore, every time the whole vehicle is changed, it needs thousands of molds worth up to millions of dollars. Plastics are used for interior, exterior, and even structural parts in the manufacturing of cars. If we look at high-end luxury cars, then their main focus is in the interior of the car. They usually require plastic with a mirror finish for the car interiors. So these plastics are manufactured using injection molding, and mold tools used for the manufacturing are highly polished. Overall, the use of plastics in the automotive sector in developed countries is continuing to grow. The proportion of plastic injection molding in total automotive molding has exceeded 60% and account for about 10 to 15% of the total mass of a car. In the future, with the pursuit of lightweight design of automobiles, the use of plastics in automotive field is expected to become larger and larger. This diagram shows the number of molds required for the manufacturing of an average car. You can see that more than 20,000 automotive parts require molds, which includes 1,500 stamping dies, 800 plastic moldings, 300 sheet metal moldings, and more than 100 die casting molds. The weight of an average car is around 800 to 1400 kg. A 10% weight reduction of car would correspond to 6 to 8% increase in fuel efficiency. A 100 kg weight reduction would correspond to 0.3 to 0.6 liter of fuel saved every 100 kilometers. This is why industries are trying to replace the die casting and sheet metal parts with plastics, as plastics are lighter. In this section, we will be looking at some applications of plastics made by injection molding in this section and have a look at what plastics are being used in the industry. This slide basically summarizes why plastics are being used in production. Plastics are not simply replacement materials, but their use is based on technical merits such as lower weight, cheaper prices, aesthetics, reduction of vibration and noise, reduced maintenance, and corrosion and chemical resistance to external factors. This slide shows the demand for thermoplastics. The standard plastics shown in the diagram refer to the plastics you see in your household. Your bottles, buckets, mobile phone covers are made using standard plastics. PE is polyethylene, PP is polypropylene, PVC, and PS is polystyrene. Engineering plastics are the plastics that you will find used for making car or airplane components. ABS is acrylonitrile butadiene styrene. ASA and SAN are alternatives for ABS. PA is polyamide, which is commonly called nylon. More detail regarding this engineering plastics will be covered in the next topic. High performance plastics are used in applications requiring very high temperature stabilities and high strength. I had previously mentioned that the weight of plastic in a car makes about 10 to 15% of its total weight. This table here shows the weight distribution of various types of plastics being used in the manufacturing of cars. You guys can take a look at the table, it's pretty self-explanatory. Since there are so many plastics available, all with different properties, the selection of the right plastic for your component should be done based on properties mentioned in this slide. Mechanical, electrical, thermal properties, how easy is the processing, is the material safe, cost, all these factors play a role in selection of the right plastic material. In the next few slides, we will be seeing car parts which are made using plastics. This slide shows the interior car parts that are injection molded plastics. The overhead systems, the interior trims, instrument panel, and steering wheel, these are all made using plastics. This slide shows the plastic parts on the car exterior. The body side claddings, headlights, fog lights, bumpers are made using plastics. Bumpers are usually made using a combination of polycarbonate and ABS. Claddings can be made using many materials, but ABS is also used for making claddings. And car headlights are also made using injection molding. Polymethyl methacrylate is the material used for headlight. This is a picture of parts under the car bonnet. Here you can see the reservoirs for the brake fluid and the coolant. Those are made from plastics. The engine oil filler cap, battery cover, and air cleaner, and in general many parts of water induction and fuel systems make use of plastics. Now there are a lot of plastics available for processing. The selection of the right plastic will be based on a number of factors mentioned in the next few slides. For any product design, there will be a number of requirements the product must meet. So the plastic with the lowest cost that matches the requirements of the product will be selected for processing. There are 6 basic divisions of the most common engineering plastics: polycarbonates, polyesters, styrenic copolymers, ABS is a styrenic copolymer, polyamides, which are nylons, PMMA, which stands for polymethyl methacrylate, commonly known as acrylics, and POM, polyoxymethylene, which commonly is known as acetyl. In the table below, I have summarized all the properties of the 6 plastic types. Here, crystallinity refers to the degree of structural order in plastics. Tg is the glass transition temperature, and Tm is the melting point. So how is the selection of plastic done? For example, let's say we are using a plastic component that will be part of some industrial machinery where the temperature can exceed 500 degrees Fahrenheit. So if the product requirement says that melting point should be above 500, then we will have to choose either polyesters or polyamides. Or let's say we want a plastic that has a clear transparent surface, then we can make use of polycarbonates or acrylics. This is why safety glasses are made using polycarbonate, and for skylights we use acrylics. So based on the properties mentioned here and the product requirement, the selection of the plastic is done. The rest of the table is pretty self-explanatory. I will pause here a moment so you guys can go through it. This slide shows some more properties for common plastics used. Weatherability is the ability of a material to withstand harsh atmospheric weather conditions. Creep is the tendency of a material to deform permanently when subjected to stresses over a long period of time. I will pause here a moment so you guys can go through the table. And this slide here shows some common applications for the various types of plastics which we have discussed. By the end of this session, you should have grasped a basic understanding of how the injection molding process works. We will be discussing the injection molding process in detail in the next session, and you should also be familiar with terms such as mold cycle, thermoplastics, and thermosets. We also discussed the plastic processing methods other than injection molding in this session, and you should also be aware of the major plastic types used in injection molding. That's it for this session. Thank you for watching the video. Hello guys, hope you are doing good. Welcome back to another session of mold design using SolidWorks. This is the second video of the series. In this session, we will be covering the product development process, various departments in mold manufacturing industries. We will be looking in detail the parts of the mold system, types of the mold system, and we will also be learning about drafts and parting lines. Before learning how the tool design works, let me give you a basic overview of how the entire plastic production process works. Initially, you have the requirements based on the customer needs that your product must fulfill. A concept sketch of the product will be created by the R&D team. Then, with reference to existing products and based on the properties required, selection of the material for the component will be done. The first draft stage refers to the creation of the CAD model for the part. Then this CAD model will be sent to the simulation team where the behavior of the component based on loading conditions and different types of analysis will be performed. Based on the results of the simulations done, the simulation team may have suggestions for improving the component, and based on those suggestions, improvements will be done on the CAD model and final simulations will be performed on it. Now, after the product to be manufactured is finalized, the design for the mold in which the product will be made starts. Now, the thing to note is that it's not necessary the entire process will be done by a single company. The product designing stage, which is till the final simulation step, may be done by one company, and then some other company may create molds for the finished product. That's why the steps from the mold design stage are shown in a different color. After the design for mold is completed, based on the CAD of the component, production of the tool starts, and then the part production can be started. Now we will have a look at the different departments in the mold manufacturing industry. First is the sales team. They take the product from OEM or product design department and quote an amount for the mold and basically handle all the talks about purchasing, selling of mold, delivery time, the price for mold and all that. Once the customer is satisfied with the price, the delivery order will be placed. Once the order has been placed, the CAD model goes to the DFM team. DFM stands for Design for Manufacturing. This department basically checks the feasibility of making the mold based on the CAD diagram. By feasibility, I mean that they will check whether the mold design for the part can be made or not and explain problems that might occur while making molds. The product design team may not be aware of the problems that might occur in mold manufacturing for the part. So the DFM department basically tells the customer what problems may occur in the mold design based on the product design provided by them. Then comes the mold flow. The purpose of mold flow department is to identify the right inlet points for the molten material. This will specify where the gates should be located. They will also analyze how the flow of material will take place. They do this by using simulation softwares that are available to check the flow of feed in the mold. They also do cooling analysis and warpage analysis. Warpage is a defect in plastic components. We will be covering defects in later sessions. Then comes the tool design team. They get the gate point location as input from the mold flow team. The tool design team decides the cooling channel location, location of ejector pins, the core cavity separation, parting lines, etc. We will have a look at what are the parts of the mold in a short while. Basically, the tool design team is responsible for all the parts of the mold tool. Then comes the CAM programming team. They basically write the programs for making the tool. Then the material for tools is ordered according to the specification given by the tool design team. Then the actual manufacturing of the tool will start using machines like CNC. Inspections include checking if the right dimensions has been achieved or not and whether the dimensions of the tools are within the tolerance. Then all the parts of the mold, the core, cavity, guide pillar and everything else is assembled. We'll have a look at all the parts of the mold shortly. Then the entire tool is assembled into the molding machine. Then the production of the parts can be started. Then the parts which are manufactured will be checked using tools like CMM. CMM is coordinate measuring machine. It's a machine for checking dimensional accuracy of components. And after the parts are checked, they can be shipped out. Here we have an animation showing how the injection molding process works. I will be running the animation first and then I will explain each part of the mold. On the right side, we can see the cavity plate and the cavity back plate. The diagram which you are looking at now is called the two-plate mold. In the two-plate mold, the cavity plate is fixed. So the right side of the system you see is fixed and only the left side, the core side of the system moves. On top of the cavity plate, you can see the guide pillars. Guide pillars are used for aligning the core and the cavity. Guide pillars will always be present on the cavity side of the mold and guide bush will be present on the core side. The length of the guide pillar should always be more than the core length so that it aligns before the core and the cavity align. On the right side, you can see the sprue and the sprue bush. A sprue is a large diameter channel through which the material enters the mold. If you look carefully, you can notice that the sprue is tapered outwards. This is done to facilitate easy removal of the part from the mold. Because as molten material flows from sprue to the cavity, there will also be solidified material at the sprue region. And if sprue is straight, then it will scrape the surface of the sprue bush and it will be more difficult to remove. This is also the exact reason why we give drafts to the components. We will be covering the topic of drafts in the later slides. Now you might also notice that a separate sprue bush is provided around the sprue. Now why is sprue bush a separate element? Because the material that is being injected from the nozzle to the sprue is very hot. The material of sprue bush is specifically pre-hardened to handle this hot material. Then we have the register rings. Register rings are provided for alignment of the entire tool with the molding machine. Don't get confused between the guide pillar and the register ring. Guide pillar is used for aligning the core and the cavity, whereas the register ring is for alignment of the entire tool with the molding machine. Then on the left of the cavity plate, you can see the core plate and the core back plate. This plate moves to the right, gets attached to the cavity plate, and then the material is injected in the region between the core and the cavity. The injected material is allowed to cool for a while, and when the part solidifies, the core plate moves back. Then we have the ejector pins. Once the part is formed and the core plate moves back, the ejector pins are used to eject the part that has been molded. The size of the ejector pins is around 6 mm. The part of the ejector pin near the core is transition fit, and then after some distance, some relief is provided for the ejector pins. The length for which transition fit is provided is called guidance of the ejector pin, and this length is around 12 mm. And then we have the return pin. The function of the return pin is to bring back the ejector plate back to the original position. The return pin may consist of a spring that gets compressed when the ejector pins move. So when the spring relaxes, the ejector system can be brought back to its original position. Then we have the spacer block here. Spacer block basically defines the distance between the core plate and the moving plate. Moving plate is the plate you see at the left end. The entire ejection system is assembled within this space. And here you have the ejector plate and the ejector back plate. The ejector back plate is driven forward by hydraulic actuators through the main machine. Rest buttons are provided behind the ejector back plate to reduce the friction that will take place if the back plate is directly placed beside the moving plate. This slide shows the surfaces formed by the core and the cavity. The surface formed by the cavity is called the A surface, and the surface formed by the core is called the B surface. The surface between the A and B surface, the surface on the thickness region, is called the C surface. We will now take a look at the actual specification diagrams of the mold assembly parts. Here you can see the diagram for the entire mold tool. On the left side, we are seeing the front view of the mold tool. The circles which you see at the edges are the guide pillars, and the small circles which you see here is used for clamping. There are some standard dimensions available for selecting the mold block. For example, let's say you need a 196 by 196 block for a mold, but one of the standard size in the market may be 200 by 200 block. So you will have to buy the 200 by 200 block and cut it to the required sizes. All the parts which we will be looking at in the mold design have some standard sizes. All the dimensions are selected based on the available standards. Here on the right, BP stands for the bottom plate, SB is the spacer block, CB is the core back plate. On right of that you have the core plate, then CV is your cavity plate, EB is the ejector back plate here, and EP is the ejector plate. This diagram shows the front view of the mold tool, and here we have the sectional view. And at the bottom you can see the transverse screw used for fixing all the individual plates. Here you can see the diagram for a guide pillar. The part of the guide pillar that enters the core when the mold is in the closed position is called the core region. In the diagram, the part of the guide pillar to the right of the yellow line is the core region. The core region of the guide pillar needs to be hardened, as it will be sliding in and out of the core thousands of times while making components. The G6 and F7 which you see here are the types of fits. The inverted triangles here denotes the surface roughness of the guide pillar. Here we can see the diagram of a guide bush. You can see that the inside surface also needs finishing, as the guide pillar will be sliding through it. The bottom part which you see here is the ejector guide pin. Its purpose is to align the entire ejector system with the core plate, and the ejector guide is surrounded by the ejector guide bush. The component on top is the return pin. In the main animation of the mold working which I showed you, this part was not included. This component is on the core side and pulls the sprue from the cavity side. The reason for the inverted taper is that more pulling force is acquired compared to a straight section. So this will ensure that the material is not cooled down at the cavity section itself, which will block the passage of the material. The tapered section which you see is also called the cold slug well. Here you see the diagram for the sprue bush. You can see that the taper for the sprue bush is 1.5 degrees. This is a standard taper for sprue. Another point to note is that the core thickness must be more than the cavity thickness. This is because the molten material will enter the core side at high pressure, and this may cause a depression at the core side. So to avoid that, we always provide a higher thickness on the core side compared to the cavity side. This is the diagram for the register ring. The center line which you see here must align with the center line of the molding machine. This is a diagram for the ejector pin. The ejector pin is also case hardened, as it will be engaging with other components in every cycle. So to reduce the wear on the part, we harden it. And this slide shows the ejector guide pillar and the ejector guide bush. So there are two types of mold present, the 2-plate mold and the 3-plate mold. The mold tool working which I explained before was the 2-plate mold. Here I will first run the animation for the 3-plate mold so you can see the working for yourself, and after that I will be explaining how the 3-plate mold is different than the 2-plate mold. The first thing to note is that there are 3 plates in the 3-plate mold, as the name suggests. The first plate which you see on the left is fixed and contains the sprue. The second plate, represented in the orange color, contains all the runners and the cavity. So in this case we see that the cavity plate is also moving, whereas in the 2-plate mold the cavity region was fixed. The third plate contains the core and the ejection system. So this part is the same as the moving plate of the 2-plate mold. We can see that the only difference in construction of the 3-plate mold is that the fixed plate of the 2-plate mold itself is split into 2 parts. And as there are 3 plates, in this case, the runner and the main part are automatically separated in the molding process. Whereas in 2-plate mold, if you remember, the material in the runner system is attached to the main part and has to be manually separated. So the advantage of the 3-plate mold is that the secondary operation of cutting the feed system is avoided. Due to this, the production time is reduced, and hence for mass productions, 3-plate mold will be preferred. However, the cost of 3-plate mold is also more compared to the 2-plate mold. So if there is an order of 500,000 components, then it doesn't make much sense to use 3-plate mold, and 2-plate molds will be used. Draft angle is an inclination from the vertical axis of the mold, or you can say a taper provided in the molds. In the case of plastic molding, a small draft angle is always provided for the components being manufactured. This is done to facilitate easy removal of components from the mold. If no draft angle is provided, then when we try to remove the material from the mold, the component will scrape the edges of the mold, as you can see in the diagram. This can damage the component and may result in scratches on the component, and in some cases it may also cause breaking or bending of the components. Zero draft angles may also result in vacuum being formed when the material is pulled, and thus more force is required to push the component out of the mold. So all the plastic parts that you see around you that were created using injection molding, all of them have drafts. The amount of draft angle that needs to be provided will depend on the polish and surface finish of the mold tools, and this polishing done will depend on the customer requirements. For example, it is more difficult to remove a textured component, so higher draft angles will be provided for textured components. And all the components that you see which have a glossy finish have been made using high polish tools, and thus lower draft angles will be required for their manufacturing. Draft angles generally used may vary from as low as 1/4 degree to 2 degrees. In this diagram, you can see how the draft angles are provided for these components. We technically can eject the parts even without providing draft angles, but then the plastic will stick in this part, and when the part is ejected, you will see scratches and marks on it. The draft angle will also depend upon the molding depth. Here in this graph, you can see that as depth increases, higher draft angles are required. But a point to note here is that it is not always possible to give higher draft angles for deep parts due to dimensional variations. For shallow parts, the draft should be around ½ degree or little more than that. For deep parts, around 1/4 of a degree draft angle may also be given if higher draft angles is not possible. Draft angles also depend upon the material properties itself. For example, it will be more difficult to eject stiffer materials, so higher draft angles are provided when working with such materials. Here you can see the draft angles given for various plastic types. This slide shows the problems that might occur if no draft angle is provided. Ejector pin marks will be present because due to no draft, more force needs to be applied by the ejector pins to eject the part, which will leave a mark on it. Ejector pin breakage, because if no draft is provided, then more force will be required to eject it, which may damage the ejector pin. Warpage is a defect that might occur because of no drafts. There will be scratches formed at the core and cavity region, and the ejector system may also bend due to no drafts. Okay, so the next topic is the parting line. The parting line is a line that splits the mold system into 2 parts. So the section formed on one side of the parting line will be the core, and the section on the other side will form the cavity. We generally try to keep the parting line in a straight line, as in a single plane. If it's not in a straight line, then it's more difficult to manufacture and assemble the mold. Now let us look at some examples showing best practices for parting lines. In the above figure, the molded product will have a mark along the parting line, but in the bottom figure, no such mark will be present as the parting line does not cut through the part. So if possible, we try to provide a parting line on the outer edge. But there may be some cases where it is not possible to provide the parting lines on the outer edge. So in those cases, you can insert a bead at the parting line section as shown in the figure. Introducing such beads along the parting lines will allow easier cutting of the gate system, and the defects also won't be very apparent. Here we see that the top and the bottom sections are misaligned. So the left top bead was offset a bit to extend it over the lower bead. In the right side part, the defect won't be as apparently visible as in the first one. So this were some tips regarding the selection of the parting line. We'll be seeing more about the parting lines and the parting surfaces when we work on the actual software. By the end of this session, you should have an understanding of how a new product development process takes place and what are the departments in the mold manufacturing industries. You should also be aware of the parts of the two-plate mold and the respective functions. We also had a look at the working of the three-plate mold, and we learnt about drafts and parting lines in this session. Hello guys, I hope you are doing good. Welcome back to another session of mold design using SolidWorks. In this session, we will be learning about machine tonnage, which will be a very short topic, and then we will mainly focus on the entire review process of plastic parts done during DFM, and then we will be covering the defects that can occur during mold design process. Now let's look at the concept of tonnage of injection molding machine. The pressure with which the molten material is injected in the injection molding machines is very high. In most of the products, the injection pressure is around 4 to 5 tons per square inch, and in some cases it can be much higher than this. So to ensure that the core and cavity do not get separated due to this high injection pressure, we have to provide proper clamping for the mold. The amount of clamping force provided by the clamping mechanism is decided by the tonnage of the machine. So for example, if we have a 100 tonnage machine, then that basically means that 100 tons of clamping force is provided by the clamping mechanism. Now it's probably easy to imagine why we can't have a very low clamping force. If the tonnage of the machine selected is very less, then the core and cavity will get separated when the material is injected and result in flashes. However, we also can't use machines with very high tonnage values. If the clamping force for the mold is too high, then it can cause defects like burns, shots, and gloss differences. Also, very high clamping force can damage the venting system, inserts, and also the core and cavity block. So the selection of the right tonnage of a machine is also very important. The clamping force can't be kept too low or too high, as both of this will cause issues. The clamping force should be within a certain range to ensure proper injection molding process. The tonnage of the machine is calculated based on the formula projected area multiplied by the injection pressure divided by 1000, where the projected area is in centimeter square and injection pressure is in kilogram per centimeter square. The projected area is the projected surface of the entire model along the tooling direction. Tooling direction is the direction along which your model is oriented and your core and your component will be moving. So let's say the projected area which we found was around 35 centimeters square, and then the injection pressure, if we use ABS material, would be around 500 kilograms per centimeter square. So if we multiply 35 by 500, which will be around 17,500, and then we divide by 1000, which will give you a value of 17.5. So 17.5 tons of clamping force will be required for this machine. But the machines available in the industry come in specific sizes. So a 17.5 tonnage machine might not be available, and in that case, you will select the closest value of the machine higher than the calculated value. For example, if you have a 15 tonnage and a 20 tonnage machine available, then you will go for a 20 tonnage machine. In this section, we will look at DFM in a bit more detail. If you remember, I had covered DFM in brief when we were discussing the departments in mold manufacturing industries. The DFM stands for Design for Manufacturing. So basically, the DFM receives the plastic component for which the mold is required by the customers or the product design team. The review of the product is done by the DFM team in terms of design, manufacturing, and molding aspects, and they also check if all data is available to proceed with the tool design. If they think that there might be some problems in creating the mold for the given product, then they convey that to the customers or the product design team. Here in this slide, I have mentioned the checklist which is followed by the DFM team to ensure that they have all the inputs required for designing the mold. I will be explaining each point in detail in the next few slides. So first we are going to cover the part details. The first point is shrinkage. Whenever the molten material in the mold solidifies, it shrinks. So the actual part size obtained is less than the size of the mold. So the size of the mold is designed in such a way that it takes into account the shrinkage of plastic and gives a part with correct dimensions. To do that, we need the exact shrinkage value for the material that is being injected into the mold. The next point is material. The material here refers to the plastic material used for making the component. And the next is number of cavities. The number of cavities required is also asked from the customers. The DFM team can make suggestions for it, but the final decision comes from the customer side. And the next point is inlet type. There are different types of gates used, and depending on what types of gates you use, there may be some marks on the final products. So the customer are informed on what are the effects of using specific types of gates, and depending on the requirement, the gate type is selected. Type of gates will be covered in detail in a separate session. The next one is surface demands. So the type of surface finish required is also asked to the customers, whether they want the surface to have a textured finish or glossy finish. If the part manufactured won't be visible from outside, then there won't be any need for polishing the tools and providing a good surface finish. For example, if you're watching this video on a PC, then you probably have a keyboard in front of you, right? Now, if you open your keyboard, then you will find many plastic parts inside it. Now, since these parts are not visible from outside, it doesn't matter what surface finish it has. Adding good surface finish requires additional cost and time and must be avoided where it's not necessary. Also, the type of surface finish required will also affect the draft angle given for the geometry. And the last point is there any engraving required? For example, you may see the company logo engraving on many products. So if engraving is required, then the details regarding the engraving is also taken from the customers. Even in engravings, for the length and width of the engraving, there are some standards to be followed. That's because these engravings are milled by CNC machines. So based on the size of the cutters that are available, there are standard engraving sizes. The parting surface is a surface that splits the core and the cavity. In most of the products manufactured by injection molding, you can see a visible mark along the parting surface. So the customers are informed that there will be a mark over here, and is that fine, or should we be changing the parting surface? On the diagram to the left, you can see a parting surface on the product. Even when using sliders, there is a visible mark along the parting line of the product. We have not covered the topic of sliders yet. We have a separate topic on sliders where I will be explaining how sliders work in detail. For now, just know that there are some cases where the core and cavity is not enough for creating a proper mold, and that sliders are added along with the core and cavity to create a proper mold. And the sliders will also leave a mark similar to the parting line. So we have to inform the customers that there will be a mark along this line. You can see the mark due to the sliders on the image on the right. For injection molded parts, there is a visible gate mark present. Most of the times the location of the gate is placed where it won't be visible from outside. But in case it is visible from the outside, the customers are also informed about these marks. You can find these gate marks on the bottom of buckets, pens, bottles, and many other household injection molded products. For the plastic components manufactured, we try to keep the overall thickness relatively constant. This is because if there is a variation in the thickness of the component, it will lead to a non-uniform shrinkage of material as thick sections shrink more compared to the thinner sections. This non-uniform shrinkage causes the component manufactured to warp. In the diagram, you can see that more warpage was observed when there was a higher change in the thickness of sections. However, when we core out the thicker section, which basically means that if we make it hollow, then warpage can be avoided. Coring out can also make the parts weaker, so sometimes ribs are added in the cored out sections to make the part stronger. Usually the thickness values used for plastic components vary from 0.6 mm to 5 mm. If we try to make parts lower than 0.6 mm thickness, then there won't be a proper filling of material in the mold. The material itself will solidify before reaching the ends. This defect also has a name. It is called the short, which will be covered in the defect section. For thickness values higher than 5 mm, gas-assisted injection molding is used. If there are deep holes in a part, then we have to make use of longer core pins to make the deep hole. But using longer pins from the core side results in heat dissipation problems. If heat dissipation does not take place properly, then it will lead to burn marks in the hole region, which is a type of defect. As a rule of thumb, if the length of the hole is greater than 7 times the diameter of the hole, then hole would be considered too deep. To counteract, we split the hole in two parts. So some part of the hole is made using the cavity side and the rest of the hole is captured from the core side. So here in the first diagram, you can see the hole, and this is the core pin used for making that hole. And in the third diagram, you can see instead of making the hole using a single core pin, some part of it was captured from the cavity side. So the cavity will be over here. This hole will be captured from the core side. Another point to note is that in general we try to avoid features in the cavity side. This is because creating these pins for holes in the cavity sides creates more surface in the cavity sides where the material can stick. Sticking of material in the core side is not as big of an issue as sticking of material in the cavity side, because on the core side we have the ejector pins to eject the part. So that's why we make the pins for capturing holes from the core side, and if the length is too large, then we make a pin from the cavity side. When we have the same upper and lower limit for tolerance, for example 10 plus and minus 1, So this means that the dimension of the component can be between 9 and 11, and we can see that both the numbers are equally spaced from 10. So this would be a case of symmetric tolerance. But if we don't have the same limits, for example 10 plus 1 minus 0.5, now the dimension has to be between 9.5 and 11. In such cases, there is a possibility that due to shrinkage, the dimension of the part may go below 9.5. So in such cases, mold is designed for a dimension of 10.25, which is the average of 9.5 and 11, to ensure that the dimension stays within the tolerance. When we close the mold, some air is trapped between the surface. Due to this trapped air, the molten material can't fill the entire mold region and some defects will be found in the finished product. To avoid this, some channels are provided in the mold to allow the air to escape. This process of providing air channels to remove the trapped air in the mold is called venting. Now, before explaining the ejector pads, I will show you what problems might occur while ejecting components with very low thickness values. In this diagram, you can see the thickness of the highlighted section over here is around 1.4 mm. However, the ejector pins come in standard sizes of 3 mm or 6 mm. So if we try to eject the component from this region over here, then that won't be possible because the ejector pin of higher thickness can't move through the core. In this specific case, this issue can be avoided by providing ejector pins over here or here, but that might not be the case in all the situations, and to deal with such situations, ejector pads is one of the solutions we can use. So here in the first video, you can see that we have a component with a low thickness value. Let's assume it to be 1.4 mm. And the size of the ejector pin is 3 mm. So this case is similar to what we saw in the previous slide, and the ejector pin will not be able to eject the part out. Here in the second video, you can see that the thickness of a specific region of the component has been increased to 3 mm. This is known as an ejector pad. By doing this, we can ensure that the ejector pin will be able to easily eject out a part of thickness lower than the ejector pin thickness. Now this would be a good time to explain the concept of undercuts in molding. Undercuts are those features in a part due to which the part cannot be directly ejected from the mold. If you see this figure on the right, you can see the top part is the core and the bottom part is the cavity. Once the material solidifies, you will notice that it is not possible to eject the part from the core due to this highlighted section. This feature is called the undercut. Now there are two types of undercuts available, internal undercut and external undercut. The diagram which you see here is an internal undercut, and this diagram here shows an external undercut. To deal with external undercuts, we use sliders. There is a separate topic where I will explain how sliders work. To deal with internal undercuts, we can use inserts, which I will explain in the next slide. So the diagram which you see here shows an insert and a part. The blue portion is the insert and the red region is the plastic component. The insert is placed at the core side of the mold. When the mold closes, the insert is present between the core and the cavity and the molten material is injected. Once the material solidifies, ejection pins eject both the part and the insert. You can see a small hole on top of the insert over here. The hole is provided for separating the insert from the part using a screw, and thus the desired part is obtained. Now here we have a diagram showing ejector inserts. Let us assume that we have a part with a large flat surface, let's say for 500 mm or something. So in this case, instead of providing multiple ejection pins to eject the part out, we can use an ejector insert for ejection of the plate. In the given figure, you can see the cross-section view of mold. The green part is the ejector pin, the blue part is the component which is molded, and the orange part which you see is the ejector insert. So this insert helps in distributing the ejection force over a larger surface without the need of providing extra ejection pins. Ejector inserts can also be used in cases where the customer does not want any ejector pin marks on the part. So in that case, an ejector insert covering a large area of the part can be used, which will help avoid the marks that would have been left if multiple smaller surface area ejector pins were used. In the last session, we saw the function of the guide pillar and its role in the overall molding operation. The left side is the core side and the right side is the cavity side. The guide pillar is used for aligning the core and the cavity. You can see there is a projection on the cavity side over here, which is called the guide cone. This is basically for interlocking the cavity and the core region. In the last session, I had mentioned that the core plate thickness is always kept more than the cavity plate, as there is a chance of deformation of the core plate due to the hot injected material. The pressure of the injected material may be around 600 to 700 bars, and to avoid any chance of deformation of the core plate, an additional support block is placed between the bottom moving plate of the mold. Now you might ask, why can't we just keep increasing the thickness of the core plate? What is the need for the support block?
It is true that the deformation problem can also be solved by increasing the thickness, but there's a limit up to which increasing the thickness is cost effective. This is because when we increase the thickness, we have increased the material cost for the core plate, and then the length of the holes which need to be milled in the core plate for the ejector pins will also increase. So that is why we use a support block instead. There are two types of cutters used for machining, the ball nose cutter and the flat cutter. Ball nose cutters are used for 3D profiles, and it takes more time for making 3D profiles. So if a parting line is along a 3D surface, then we need to make a 3D profile that would require more time. So that's also one of the reasons why we try to make the parting line in the same plane. When we use ball nose cutters for machining sharp corners, it produces a fillet at the corner, as you can see on the right side of the slide. The creation of this fillet makes it difficult to match the core and the cavity side. So that is why some relief is provided near sharp corners near the mating surfaces. In some cases, if the length of the rib is very long, then it gets difficult to eject the rib from the mold because the plastic sticks to the wall of the cavity. For such cases, we make use of free play inserts. In the first diagram, you can see the cavity region and the part formed within it through injection molding. The yellow is the part and this is the cavity region. Now if the length of this rib is more, then it would be more difficult to eject it out of the mold. In such cases, a free play insert is added. The purple section you see here in the diagram is the free play insert. The free play insert is present in the cavity section. When the material is formed through injection molding, a screw which you see at the top drives the free play insert in downwards direction, which in turn pushes the part out of the cavity. If the length of the plastic part manufactured is more, then we provide multiple gates for the part. The exact length after which we need to provide an additional gate depends on a material property called as flow length. Flow length is the distance after which the molten material will solidify. So for example, in the diagram below, let's assume the length of the part to be around 1500 mm. And let's say we know that for the given wall thickness, the flow length is 250 mm. So here, since the length of the part is more than the flow length, we will have to provide additional gates. So if we think of providing 8 gates, we can check that 1500, the total length divided by 8 would be some value between 180-190 if I am not wrong. And since this value would be less than the flow length of the material, there shouldn't be any freezing of material due to an inadequate number of gates. So this is how the number of gates is selected based on the flow length of material.
Now we will look at the concept of balancing of mold block. The pressure of the injected material in the mold is very high and proper clamping needs to be provided to ensure that proper injection molding takes place. Remember I mentioned earlier that we select a specific tonnage of machine that decides the clamping force acting on the machine. This clamping force provided exerts an equal amount of force at all the ends of the machine. The diagram which you see on the left is the side view of the mold. You can see the runner, cavity and the mold block. And on the right you can see the same mold block in an isometric view. In the first case, you can see the runner is at the center of the mold. So when the molten material is injected into the mold, there will be a force at the center of the mold blocks which will try to separate the mold blocks from each other. This force is denoted by the letter F in the diagram. And since we don't want the mold blocks to get separated, an equal clamping force will be exerted equally from all ends to counteract the pressure of molten plastic. This clamping force is represented by the letter P, and the value for this will be calculated based on the formula for calculating the tonnage of the machine. So since the opposing force at the center is balanced by the clamping force at the ends, the first mold is said to be balanced and will function properly. Now let's look at the second case. Let's say we can't provide the gate location at the top and we have to provide the gate location at some other face. So if we provide a runner as shown in the second diagram, then the point at which the injected material creates an opposing force will also change, and it will be near the ends as shown in the right diagram. Now, as the opposing force is not at the center, one side of the mold will require a higher clamping force and the other side will require less clamping force. And since it is not possible to have different clamping forces at each end, there will be some points in the mold where the clamping force is too high or too low, and we can't have either of these cases. So this is called an unbalanced mold and we can't use this. So what else can we do to keep the mold balanced and also have the gate location at the same point as second case? In the third case, you can see that the size of the mold block itself is increased in order to keep the sprue at the center. So in this case, the molten material injected will exert an equal force on all ends, and the clamping force will also exert a constant equal force at all ends to counteract this force. And the mold will be balanced in this case. So the thing to note is that the sprue location should always be at the center of the mold. So for single cavity tools, we try to go for case 1 as it is balanced, and the material cost and runner length is also less in case 1. But in case we can't go for case 1 due to gate location constraints, then we can go for case 3. In case of multi-cavity tools, we always go for case 3. Here you can add a second cavity to the same mold and have a 2-cavity mold.
If we have a part with a slot in the center, then we can place the gate location at the center of the part as shown by the blue arrow in the diagram, instead of outside the part as shown by the red arrow in the diagram. The blue arrow case is similar to case 1 which we saw in balancing, and the red arrow is similar to case 3 which we saw in balancing. So providing the inlet from the center will reduce the runner channel length and help in reducing costs of runner channels and also reduce material wastage. Another point to note is that generally a better surface finish will be given on the cavity side compared to the core side. Also, the draft angles on the cavity sides are more than the draft angles on the core side. This is done to ensure that the plastic does not stick to the walls of the cavity. If you remember the working of the mold, I had mentioned that the cavity side is fixed and the core side is moving for the 2-plate mold. So when the core moves away from the cavity after the part is formed, the part should come along with the core where it is ejected using the ejection pins. The part should not stick to the cavity walls when the core plate moves back. So to ensure that the part does not stick to the cavity, better surface finish and higher drafts are given on the cavity side. In the diagram, the polished grain 320 and medium glass blast are types of surface finish. The polished grain finish is a better surface finish compared to the glass blast. In the diagram shown, if we provide the gate location at the center over here, you can see that some regions of the mold will fill earlier compared to other regions. The walls nearest to the gate point will be filled first, and the walls farthest from the gate point will fill last. But what if we want a uniform flow over the part? To achieve that, we can make use of flow leaders. Flow leaders are the specific regions in a part that are purposely made thicker to promote the flow of the material. The flow of material will increase in the regions of higher thickness, which will help us achieve an overall uniform flow of material. Now we will be looking at some of the defects which can occur in the molding process. Here all the defects are mentioned that I will be covering in this session. The first one we are looking at is the short shot. Now to acquire a component with correct dimensions, the molten material must completely fill the cavity region. But in some cases this does not happen. In the diagram you can see that there are some regions where the flow of material did not take place. So what you see here is the short shot. A short shot is the incomplete filling of the mold cavity which results in the production of an incomplete part. Now this can happen due to a number of reasons. It is possible that the amount of material injected into the mold itself is not sufficient to fill the entire mold, or it is also possible that the pressure of the injected material is not sufficient to flow through the entire cavity. If proper vents are not provided, then the air would be trapped in some regions and then the material might not be able to completely fill it. Also, if the size of the gates is very small, or in regions with thin cross sections, the material may freeze before filling the entire cavity region, resulting in a short shot. Flash is the excess material that you will find attached to your component. Now this can happen when the core and cavity plate do not close properly, or the injection pressure is too high and the material seeps outside the mold. To fix this issue, we have to do some post-processing operations which will increase the production time. When two molten material flow fronts meet at a specific point, it creates a visible partition in the surface. This defect is known as a weld line. The component is especially weaker in the weld line and will easily break if force is applied along this weld line. In the diagram below, you see how weld lines are formed by changing the position and number of gates. In the first case, you can see that a single gate is used at the edge. This will create a single weld line in the region opposite to the gate point. In the second diagram, you can see 4 gates are used, which led to creation of 4 weld lines. Now since weld line is a type of defect as the component is weaker along the weld line, but here case 2 is better than case 1. This is because the component will be a lot weaker along the single weld line in first case compared to the weld lines in the second case. This weld line formed in the first case is called as a weak weld line, and the weld line in the second case is called as strong weld line. In case 3, you can see that the position of the gate was changed such that no weld lines would be formed. So as far the strength of the component is considered, case 3 provides the best flow of material in cavity. However, due to customer requirements, it might not always be possible to give the gate point in that location. Now we will look at the sink marks. Sometimes due to the shrinkage of the material at areas with higher thickness, a small crater or depression is formed. So the customers are informed of any possible sink marks that may appear due to the current dimensions of the product. We usually see this effects around the ribs. The rib thickness is usually kept around 0.5 to 0.7 times the thickness of the part to reduce the chances of sink marks appearing. Sometimes during the molding process, air might be trapped between the molten material, which will result in the formation of blisters. It is also possible that the feed material used is not dry enough, and while heating the material, it results in formation of steam, creating pockets of trapped air. Blisters affect the component aesthetics and also weakens the component.
Now we will look at jetting. When the molten material is passed through the gate with a very high pressure, it is sometimes possible that instead of uniformly filling the cavity section, the flow will have a wavy snake-like pattern which you see here. This is not a desirable way of molten material filling the cavity, as this leads to weak parts and also many internal defects. So if we have a case where jetting may occur, then we can either increase the gate area or change the position of the gate, as you can see in this diagram, so that a more uniform flow occurs throughout the cavity. Here, as the material flows through the runner and the gate, due to the position of the gate, the material will completely fill the left region before moving on to the right part, and thus a more uniform flow will be achieved. Whether a change in the gate location will be needed or not to prevent jetting is usually found out by mold flow analysis, and then the mold designer has to design the gate accordingly.
In injection molded products, you will sometimes notice a charred or a burnt dark plastic region. This is called as a burn mark. This can happen when the temperature of the molten material injected is very high. Burn marks can also occur when the air trapped in the cavity overheats instead of escaping out of the system. So controlling the temperature of molten material and providing proper venting usually fixes this defect. Warpage is a defect in which the shape of the component deviates from the required shape. This happens when there is an uneven shrinkage of material which occurs due to uneven cooling of the material in the mold. There can be many reasons due to which warpage occurs. Some of the reasons could be non-uniform wall thickness in the cavity or improper cooling channels. In injection molded parts, you will sometimes notice that some regions have a better surface finish compared to other regions. This results in a visible gloss difference in the product. This can happen due to improper surface finish of the mold tool itself, or it can also occur due to shrinking differences, or there might even be an issue with the raw material being used. Hesitation is a defect in which the flow of material along a specific direction slows down or completely stops. In case 1 below, you can see that the material is not being filled in the rib section. This is because the molten material follows the path of least resistance and fills the region with more thickness first compared to regions with lower thickness. That is why this defect is most common in areas with ribs or other areas with lower thickness values. This defect can be avoided by providing proper gate locations, as you can see in the second diagram. Overpacking is a defect in which more material is concentrated in specific regions compared to other areas. In the diagram below, you can see that due to the positioning of the gate, more material is being concentrated on the left side compared to the right side of the part. This will result in non-uniform shrinkage of the material and also non-uniform density in the overall part. The selection of the right gate location should solve the issue of overpacking. Unbalanced flow. We say that the flow is unbalanced when some extremities of the mold fill earlier compared to others. If all the ends fill at the same time, then it is called a balanced flow. Unbalanced flow can result in many issues such as warpage, density differences, and higher cycle time. Flow leaders, which I mentioned in the previous section, can be used to acquire a more balanced flow throughout the mold. So in this session, we learnt about the machine tonnage. We saw the points that are taken into consideration by the DFM team before starting the mold design. And we also had a look at the defects which can occur during the molding process. And that's it for this session. Thank you for watching the video.
Hello guys, I hope you are doing good. Welcome back to another session of mold design using SolidWorks. In this session, we will mainly be focusing on parting surfaces. I will explain what parting surfaces are, the various types of parting surfaces, and we will also look at some example cases and understand the selection of parting surfaces. And after that, we will also cover the concepts of matching draft, shrinkage, and core cavity inserts. So first, we will start by understanding what a parting surface is. In the second session, I had given you a brief explanation of what a parting line is. I had mentioned that the parting line is the line that splits the mold into two parts, that is the core and the cavity. The concept of parting surface is the same as that of parting line. The parting surface is the surface that splits the mold block into two parts, the core and the cavity. I will elaborate on this point a little by using the model which I created. So let's take this simple model for understanding where exactly does the parting surface lie in the mold. This model which you see is hollow, as you can see in the image on the right. So let's say I want to create a mold for making this part. So I will first select a parting line for the mold. In the figure you can see the parting line is indicated by the blue line. Now according to the location of the parting line, a parting surface will be formed. In the diagram, the blue surface is the parting surface for the mold. So this is the surface where the core and the cavity for the model will meet. The portion of the mold block above the light blue surface will form the cavity, and the portion of the mold block below the blue surface will form the core. Here I have an image showing the core and the cavity for the part, and during the injection molding process, these two blocks will come into contact with each other. So the surface where these two blocks are touching each other, which is displayed by the highlighted blue surface, is the parting surface for the mold. So in the previous slide, what we saw is called the flat parting surface. But all the parting surfaces are not similar. Based on the different contours or profile of the part, the shape of the parting surface changes, and it has been classified into 4 different types. The flat or straight parting surface, stepped parting surface, angled parting surface, and the profiled parting surface. I will be explaining each type in the further slides. So here we have a part that will have a flat parting surface. On the right you can see the core and the cavity for the part, and the green line indicates the parting surface where the core and the cavity blocks will meet. So whenever you have this type of flat surface, it is called a flat or a straight parting surface. Machining of this kind of surface is the easiest, and that is why flat parting surfaces are preferred over other types of parting surface. But it is not always possible to provide a flat parting surface, as we will see in the further slides. Here we have a model similar to the previous one, but in this case the base of the model is not in the same plane. So we can't have a flat parting surface in this case. On the right, you can see what the core and the cavity will look like for this model. The green line again indicates the parting surface for the model, and you will notice that though the parting surface is still flat, but it is located in 2 separate planes. So this type of parting surface is called the stepped parting surface. Now here we again have a similar component, but this time the base of the component is at some angle. So again we can't have a flat horizontal parting surface for this part, and the core cavity mold blocks will be at some angle, as you can see in the image. But the thing to note here is that even if we have an angled parting surface, the entire mold block won't be created at an angle as shown in the image. Instead of that, as you can see in the bottom image, the inclined profile of the component will be followed only up to some distance, which is usually somewhere around 20 to 30 mm, and then the blocks are made flat again. This is done because, as I mentioned earlier, machining is easier if we have a flat horizontal surface. And once the profile of the component is captured in the mold block, there is no further point in continuing the same angled surface. Even if you have the complete mold block at some angle, or if you have the mold block at some angle close to the component and then a flat profile, the end result as far the molding of the component is considered will still be the same. This addition of flat surface instead of angled surface is done only to allow easier machining. And another point is, if in actual practice we were creating a mold for this component, then we would be providing some relief in the highlighted region. So that basically means that the core and cavity blocks won't come into contact in this region. Now this is done in order to avoid the rubbing of the core and cavity blocks. In the rest of the parting surface, the core and the cavity blocks do come into contact, but as the core is moving away from the cavity, the blocks get instantly separated and there is no rubbing of the mold blocks. But in the highlighted region, the surface is at a 90-degree angle. So here, as the core block moves away from the cavity, it will rub the cavity block, and over time it will damage the mold blocks. In general, we try to avoid steel-to-steel rubbing in mold blocks, so that is why a relief is provided to avoid damage to the blocks. And here we have a part that would require a profile parting surface. You can see the base of the part has a curvature, and if we want the molded component to have a curved base, then you have to create a curved mold block for that. So whenever you have a curved profile like this case, we will have to create a curved or a profile parting surface. And as I mentioned previously, we don't need to make the entire mold block with a curved profile. We will have the curved profile close to the component, and after that we can have a straight parting surface as shown in the figure for easier machining. Now we will be looking at some example cases and understand the selection of parting surfaces for these parts. Since the parting surface defines the mold blocks for a mold, selection of parting surface will also affect the difficulty in creating the mold for the part. I will explain this point using the hexagonal component which you see on the top right. So the blue part which you see is the component to be manufactured. And on the left and the right, you can see two different parting surfaces for this model. In the left case, you can see that once the component is molded, the core can easily move to the left and the part can come along with the core. But in the right case, due to the selection of the parting surface as shown in the figure, the part cannot move along with the core. It will get stuck in the cavity. This is because due to the selection of the parting surface on the end, an undercut has been formed in the second case, which is denoted by the red color. So here you can see how the selection of parting surface can increase or decrease the difficulty of demolding process. The selection of parting surface should be such that a minimum number of undercuts are formed and the demolding process is also simple. For this specific model, the selection of the parting surface as shown in the left diagram is more preferable. Now here we have a case showing where the angled parting surface would be more preferable. You can see the example component on the top right. First, let's have a look on the left case where a straight parting surface was used. Here the blue colored part is the component and the green color indicates the parting surface. In this case, the parting surface was selected along the flat base of the component. But once the material is injected and solidified, if we try to remove the part from the mold, it won't be possible due to undercuts, which is indicated by the red color. Now let's look at the second case. In the second case, an angled parting surface is selected instead of a straight parting surface. And you can see that due to this selection, there are no undercuts present in the model now, and it can be easily ejected from the mold. Since the machining of straight parting surfaces is easier, if possible we try to avoid other types of parting surface and always go for the straight parting surface. But in this case, use of angled parting surface helps us in avoiding undercuts which cannot be achieved using the straight parting surface. So for this specific model, use of angled parting surface is the preferred method for designing the mold. Here we have another example where we will have to use the profile parting surface. As the base of the spoon is not along a single plane, we will have to use a parting surface that is along the profile of the spoon. If you take any plastic spoon, you will notice a parting line along the spoon profile as you can see in the image. And the red lines which you see indicates the inlet for material injection into the mold. Here we have another example where angled parting surface will be used. In this case, let's assume the material injection to happen along the path shown in the red. In this case, what will happen is, as the injection pressure of the molten plastic is very high, it will push the upper cavity block towards the left, and if that happens, the part dimensions won't be accurate. So in cases like this, a similar angle profile in the opposite direction would be made on the block to lock the core cavity blocks as shown in the diagram. So this locking issue would only happen if we are molding only one component. If we were molding two components together, then the mold block would look something like this. So here we don't have to worry about the blocks moving in the horizontal direction. The inlet of the molten material will happen from the center, which is shown in red in the diagram, and the forces on both the sides will be balanced. Now let's have a look at another example. Let's say I want to create a mold for the part which you see here. So here there are two images showing two different parting surfaces. In both the cases we have a flat parting surface, and in both the cases there won't be any undercuts in the model. So as far the ease of demolding and machining is concerned, there is no difference between the two parting surfaces. But in case 1, the selection of the parting surface is such that it will leave a mark on the model as you can see in the image. So in this case, parting surface on the right side will be preferred just because there won't be a visible parting line in the final model. The selection of the parting surface between these two cases is made purely on aesthetic basis. Now I would like to explain the concept of matching draft. to explain this concept, I will be using a model which you can see here, and I have also created another model with a slight modification which you see here. The difference between the two models is that the left one has a 90-degree cut in the groove, whereas in the second one there is a small inclination as you can see in the image. And I have also created the core and the cavity blocks for the model, and you can also see the assembled mold block for the model. So here let's focus on the side view of the mold block for both the blocks. In the left case, where we have a 90-degree cut groove, when the core block tries to move in the downwards direction after the plastic material is solidified, the core steel block will rub against the steel cavity block as you can see in the animation. So when this process takes place repeatedly, the core cavity blocks will get damaged, and once the blocks are damaged, the plastic material will seep through the cracks in the mold blocks, resulting in flashes. Flashes is the defect where the extra material is formed along with the component. But in the right case, since the cut is inclined, there won't be any rubbing of the core blocks. When the core block moves downwards, it will immediately get separated from the cavity block. Now, this concept is similar to the concept of drafts for plastic parts that I had explained previously. But here we are talking about the steel mold blocks and not the plastic part. For plastic parts, I had mentioned that there should be at least 1/4 to half a degree of draft. That point was for plastic to steel contact. The concept of matching drafts is for steel to steel contact. The rubbing of core and cavity blocks is an even bigger issue, and the rubbing of core cavity blocks won't happen in all of the models. But in the models where it does occur, like the model which we are discussing, we need to have at least 7 degrees of inclination so that the steel blocks don't rub against each other. So let's go back to the previous model with the 90-degree cut. So if you get a part like this for mold design, you should notice that there is a side groove in the model which has a 90-degree cut. This would in turn mean that if we try to make a mold for this block, then the mold blocks will get damaged over time. So as a mold designer, you are supposed to tell the product design team or the customer that there are no adequate matching drafts in the given model and a revision of design is required. You can also suggest that an inclination of 7 degrees can be added to make the diagram look like the second image. And once you receive the product with adequate matching draft, you can proceed with the mold design. Now there is another thing that I would like to explain here. While explaining the angled parting surface, I had mentioned that we don't follow the profile of the component throughout the entire mold block to ensure easier machining. Similarly, in this case too, we won't follow the groove profile throughout the mold block as you can see in the diagram here. The image may appear glitched, but it's not. It's directly taken from SolidWorks. This is how overlapping surfaces look in SolidWorks. In this case too, similar to the angled parting surface, we will follow the profile of the component till some distance, usually 25 to 30 mm, and then we will make it as a flat parting surface as you can see in the diagram. And in this case too, we will be providing a relief where the core and the cavity blocks have a 90-degree profile as you can see in the sectional view of the mold block. The relief is provided so the core block does not rub with the cavity block when it moves in the downward direction. Now let's look at the concept of shrinkage. I had explained the concept of shrinkage in brief during the DFM session, but here I will be elaborating on the same topic. For explaining the shrinkage, I will be using the same model which I had used for explaining the straight parting surface. Let's say you're given this model with all the dimensions and you're assigned the task of creating a mold for it. Now, if you create mold blocks for the same dimension as shown in the figure, then once the molten plastic material gets solidified, the component will shrink and the final part which you obtain will be even lesser in size compared to what you see in the diagram. In order to avoid this problem, we always create a mold for a model size bigger than what is actually desired, as you can see in the image. Now, you might wonder how we will know the exact increment in size of the mold to account for the shrinkage. For that, as a mold designer, you will always get information regarding the material that will be injected in the mold and the shrinkage value for that material. Shrinkage value is a material property and the value of shrinkage is always fixed for a specific material. For example, let's say the product design team has mentioned that the plastic material they are using for the component has a shrinkage value of 0.5%. So in order to account for the shrinkage of the component in the mold, you will have to create a mold for a component that is 0.5% bigger than the desired component. In the right diagram which I have created, all the dimensions are 0.5% bigger than the desired dimensions what you see on the left. If you want to confirm the values on the right, then you can convert the percentage value into fraction by dividing 100 and then add the value of 1 to get the factor by which you need to increase the value. So for 0.5% shrinkage, you will divide 0.5 by 100 and you will get 0.005. Add 1 to it, the value becomes 1.005. So 1.005 is the scale factor, and all the values which you see on the right is the product of the original dimensions and 1.005. Now I will be explaining the concept of core and cavity inserts. Here again I am going to use the same component to explain the concept. First, I would like you to focus on the left diagram. Here we have a normal core and the cavity, as we have seen multiple times throughout this course. But the thing to notice here is that the entire core and the entire cavity block is formed using a single material. When the core and the cavity profiles are cut in a single large block, it is known as an integral core and cavity block. Now let's look at the second case. Here, 2 blocks are used on the core side and 2 blocks on the cavity side. There is a smaller red and green color block which has the profile of the part, and then there are large grey flat blocks around it. So here the core and cavity blocks are not made up of a single integral block. The grey part is a separate block and the red block is inserted into the grey block so that the 2 blocks together function as the complete core block. So as far the functioning of the core and the cavity is considered, both the integral and the core cavity insert mold blocks produce the same results. So why do we need the insert blocks separately? That's because as we keep creating plastic components in the mold, over time the blocks may wear out or get damaged. So in the first case where we use the integral block, the entire core and cavity block will have to be replaced when the mold blocks wear out. But in the second case, once the core and cavity insert gets worn out, only the insert will be replaced by another insert instead of replacing the entire block. This helps in reducing the overall cost of injection molding. In actual practice, the inserts are made using high-grade steel and the remaining blocks are made using lower-grade steel to further reduce the cost of the mold. Now these inserts are only used in the final mold, which is used in the actual production process. When we are designing the mold for the first time, that design is only for creating prototype products, and anyways high-grade steels are not used for creating molds for prototype products. So during the initial design of the mold, you don't need to create these inserts taking cost reduction into account. So in the SolidWorks session 2, I probably won't be creating these inserts. We might create inserts in some cases, but that won't be for the reason of reducing the cost. It will be for a different reason, and I will explain that in SolidWorks session itself. So in this session, we covered the parting surface, we looked at various types of parting surfaces, and we also saw some example cases to understand the selection of the parting surface. After that, we also learnt about matching drafts, shrinkage, and core cavity inserts. And that's it for this session. Thank you for watching the video.